Ampere's Law. Consider an infinitely long coaxial transmission. I love that word. And we have a love-hate relationship. Coaxial transmission line carrying a uniformly distributed current I in the center conductor and negative I in the outer conductor as shown below. The inner conductor has a radius A and the outer conductor has a radius B and outer radius C. Using Ampere's law, find the magnetic field intensity H for 0 is less than rho less than or equal to 5A if B equals 3A. Okay. So, couple interesting points here. So, we're asked for magnetic field H. I grew up just learning using B instead of H. B and H mean the same thing when you're not talking about magnetization. So basically, if you're magnetizing the material, then there's going to be a difference. But otherwise, they're pretty much the same thing. So like the idea is you have like a coil of wire and you stick a nail in it. That nail is iron. It helps magnetize and it'll change how your solenoid works with an iron core. And that's when you'll need difference between H and B. But normally, if you're just working in a vacuum without magnetization, then H will be B over mu naught. And they both are measuring magnetic fields. They're just doing it slightly differently. So I'm going to find things in terms of B, but then you could just take magnetic field B divided by mu naught, and you'll have the answer for H, since this really isn't talking about magnetization at all. And I'm pretty much going to ignore the B and C and just write everything in terms of A, since I think it's simpler. So we're given various R's where we're trying to find it for R less than A. I'll say 0 less than R. And then we find it between A less than R less than, was it 3A? 3A. Then we have 3A less than R less than 4A. And we probably have then 4A less than R less than 5A, where I'm just using R instead of rho. I like R for radius. It's a personal preference. You can use rho. Not a big deal. So, start off by writing up Ampere's law. So we have B dot dl equals I enclosed times mu naught. Maybe you should have the mu naught of, it's okay. It's fine the way it is. Okay. So the idea here then is we are going to draw, before with Gauss's law, we would draw a three-dimensional shape. Now here, we're going to draw, I guess, a two-dimensional shape. So with Gauss's law, we'd do a three-dimensional shape with a surface area. Now we're going to draw a two-dimensional shape with a length. So we draw like a circle, because we have a dot product here, and ideally we want the B field and the length of the shape going along the direction of the shape to be either parallel or perpendicular. If they're parallel, then the angle between the two, cosine of theta, will be cosine of 0, which will be 1, which is good. Or if they're perpendicular, then cosine of pi over 2 would be 0, and everything cancels out. So we're going to choose our area, our circle, to be like this. I'm going to draw it like that, but for our first circle, it's actually going to be inside the inner coaxial cable, inner conductor. And we're assuming a uniform charge here. If you've heard of the skin effect, basically it's where all the electrical charge is just at the outside of a conductor and it's very thin, kind of like, skin. That applies to alternating current, not direct current. And I'm assuming that since we're given just an I here, which we assume is constant, then this would just be direct current. So your thought process might be like, oh, there's no current actually on the inside, skin effect, etc., etc. It's a good thought, but it's not what applies here. So we're assuming uniform current like water, more or less, through a pipe. Okay, so we'll do our simplifications. We'll work through this. So magnetic field, it's going to be the way of knowing magnetic field is for a wire is if you have a wire like this, current going that way, you put your thumb up this way and you wrap your fingers around that way. And the direction you wrap your fingers, so thumb in direction of current, and then wrap your fingers, the way you wrap your fingers would then give you the direction of the magnetic field. So the magnetic field will be going, let's say the current is coming out at us, the magnetic field in this case would then be, using the right hand rule, like this, wrap your fingers around. Not quite sure how the camera angle works, that's okay. The magnetic field would be that way. So if we draw the circle that way, then they'll be aligned with each other, and this dot product then becomes integral B times dl. Well, where that's a times, not a dot product. I'll just do it this way. There we go. Not vectors. And since the B will be, the magnetic field will be the same radius the whole time, we can then factor it out. And so now this is just the circumference of our circle equals I enclosed time, well, I'll do it this way. Mu naught first, then I enclosed. There we go. That seems reasonable. All over integral dot dl. Oh, I divided by the integral dot dl. So now we're just going to look at this for all of these cases right here. So that's the, I guess, derivation, justification. Erase this, move this over, rewrite my B for magnetic field. We have B equals, and so when we have, when we're looking within the inner circle here, our I enclosed will be proportional to the circle here. So we have mu naught over our 2 pi r, yep, 2 pi r, where r is less than a, and then the amount of enclosed current would just be the fraction of 2 pi r over 2 pi, no, over, so we're looking at this, so we basically have two circles here. We have this circle and we have this circle here. And we're trying to, this will be our inner circle, and we want to find out the ratio of the areas. And so the ratio of the top of the area that we're looking at would be pi r squared, and then the ratio of the total would be pi a squared. So big circle, pi a squared, small circle, pi r squared, and we do pi r squared divided by pi a squared, and that gives us our enclosed current, which kind of makes sense because, and then we'll multiply this by I, the total current going through. So if our radius is 0, then we'd have 0 over some number. 0 times I means we'd have 0 current. But if our smaller circle is the exact same size as the bigger circle, we'd have pi a squared over pi a squared, which would be 1, which means we'd have all the current, which makes sense. Okay. Do some canceling. So one of these r's will disappear, one of the pi's will disappear, and we're left with mu naught r over 2 pi a squared. So this is basically saying that as our radius gets bigger, we get more and more magnetic field, which makes sense because we're still in the wire. As we're getting bigger, we're picking up more current. So this would be mu naught r over 2 pi a squared. Excellent. And then if you want to convert this to h, you basically divide by mu naught, which means that mu naught goes away. So now we're going to look for the area between the two. So now, once we get past the maximum size of the interior wire, it doesn't matter how much bigger we get, we're not going to pick up any more enclosed current. And so, I'm going to get rid of this. We are now going to have the situation of where we're going to have mu naught, and then I enclosed is going to be I. Ooh, I think I forgot to multiply this by I. Yes. Forgot to multiply that one by I. Good catch. Thank you. All over 2 pi r, which is our the circumference of our Amperian loop. I think it's Amperian loop is the phrase that's used. So bum bum bum. Yes. Yep. I'll just rewrite the same thing. So our answer for this one, where the radius is between a and 3a, we just get mu naught I over 2 pi r. And the magnetic field will decrease as 1 over r now, because as we're getting bigger, we're not picking up more enclosed current. So now we get to the next one, where we're going to have mu naught I enclosed. So we're somewhere between the within the outer ring now. Mu naught I enclosed over 2 pi r. So this is from the inner coaxial, but then we're going to want to subtract off, since it's going in the opposite direction, the magnetic field produced by the outer ring. And so that will follow the same format we have up here. So mu naught all over 2 pi r, because the radius will be the same. But we need to now figure out what this I enclosed is. And this I enclosed will be something like, we have a circle like this, which is our r distance. And then we'll have another circle around it. So this goes up to 3a. Oh, there's a 4a. This is 4a. This is 3a. R is between it. And so we kind of have this ring, and we have to find out the ratio of our, I guess, in-between ring versus the whole ring. So, and we should get a number between 0 and 1. And so I'm going to find the area of the inner ring, which would be, I guess it would be, wait a sec. So the area of this, of our big one, would be pi r squared, because pi r squared is the area of a circle. But then we'd want to subtract off 3a squared, which is the interior of the ring. And then the area of the bigger ring, the 3a to 4a ring, would be 4a squared, no, pi r squared, pi 3a squared. There we go. Whoop, whoop, green. The big ring would be pi 4a quantity squared minus pi 3a quantity squared. Because you see how they both have this pi 3a squared on the bottom. Okay, so now we have, simplify this slightly, pi times r squared minus 9a squared all over pi times, see, it's 16a squared minus 9a squared. So the pi's will cancel, and we're left with r squared minus 9a squared all over 7a squared. 16 minus 9 is 7 times, and then this will be r squared minus 9a squared all over 7a squared. I know it looks really confusing at this point, but you got to think we're kind of in a confusing spot because we're totally enclosing the center interior line, but we're only partially through the secondary cylindrical shell. Okay, and so that would be the answer for, get rid of this guy real quick. Kapow. Nope. Yes. Line. Okay, and so now the 4a to 5a, we're going to look at the same thing we had over here, right here. And we're just going to do the idea of mu naught I enclosed all over the Amperian loop that we draw that encloses everything. It's outside the entire coaxial cable, all over the circumference of said Amperian loop. Well, we know that we have a positive I and a negative I, and so when we add those currents together, we get 0. That gives us an entire current enclosed of 0. Therefore, the magnetic field outside of this coaxial cable will be 0. And that's because we have these competing currents going in opposite directions. So that's how you find the yes. That's where we get the magnetic fields throughout this coaxial cable. Right? I'm going to clean up the board a little bit. I'm going to leave Amperes Law though, because I think we'll use that for the second one as well. Reduce the color there. Take this guy, move it over, straighten him out slightly because I'm right-handed. Very right-handed. Okay. And again, if you want to convert, I used B for magnetic field instead of H. There is a mu naught conversion factor there. Okay. Consider an infinitely long circular hollow cylinder of radius A. Okay, shown this right here, radius A, carrying a surface current density of that. Okay. Using Ampere's law, find the magnetic field intensity inside the cylinder. Assume the magnetic field outside the cylinder is 0. Okay. So this is basically a solenoid. You've probably seen the idea of a solenoid before. It's just a coil of wire. So you really can't get current to flow like this with just a solid. I guess you probably could. There's probably some way to technically make it work. But you really don't see it very much in reality. The way you do something similar to this is you have a coil of wire, it goes through here, and then it loops through and finally gets to the other end. And that looping is what gives you this flow along the edges like this. And your first thought is, well, we do the same thing we did above. We do a little Amperian loop in the middle. We have Q enclosed, and not Q enclosed, we have a current enclosed of 0 since there's no current flowing in this loop, and we get 0 closed current, therefore we have 0 magnetic field. Yeah, I'm not quite sure why it doesn't work that way, but it doesn't. So I'm going to draw the cylinder on its side like this. So this is the cylinder, and I'm going to draw these just kind of like, okay, here's the equivalent of a solenoid. And what we're going to do then for our Gaussian or Amperian loop is we're going to draw it like this. So it'd be something like this, cutting on going into the inside. My artistic skills are terribly lacking. So Amperian loop right there, coming in, and then it cuts through the center, like so. And so the only part that experiences current is this portion right here. So if we look at how these wires are kind of cut by our shape here, we have wires like this, and they're either going in or out. And so when we do this integral here, and we look at the current enclosed, you have these three segments of our Amperian loop that include a current. And your thought process might be, well, how do we count for these sides? Well, we let them cancel each other out because our Amperian loop has a direction, and these two sides will go in the opposite direction. So the only side we're concerned with is this side right here. So all we have is this length here, and this one, since they're going in opposite directions, will cancel each other out with respect to this current. long story short, we get something along the lines of, so look at this I enclosed real quick. We have a current charge density. And so I'm going to rewrite that as a linear charge density. So I'm going to say lambda, linear charge density, equals a certain amount of current. I? Yeah, I'll say I. Maybe I should say A for amps. I'm not sure. I'll do big I. Small I, or big I. Small amount of big I for a small amount of length. And so then when we rearrange this and integrate, we find that the current equals lambda times the length. And the reason I'm going to say this is a linear charge density, because it's kind of like the amount of, so if you have current flowing this way, or this way as shown, the more length of this cylinder that you're looking at, the more current you're going to get. Therefore, it seems to me to make sense to look at this as a linear charge density, basically how much length of the cylinder you're looking at. So then we go over here and we rewrite this I enclosed as a mu naught lambda L, and we'll assume that this is infinitely long, and then we want to find the length of this portion right here, which is just L. The lengths will cancel. We're left with mu naught lambda, where this will probably look different than if you look for the definition of a magnetic field due to a solenoid, but then this lambda right here encompasses a lot more than it's usually given in each of the variables of the formula you're going to look up. So what this is saying is mu naught will be a so the magnetic field will be mu naught times the surface current density. And usually when you see for a solenoid, the magnetic field due to a solenoid is usually mu naught, I think, N over L times I. So this N over L times I is basically what this all-encompassed, this right here is the same as our lambda. So long story short, the answer to this then will be magnetic field on the interior will be mu naught lambda. And you probably want to have a direction with that. The right-hand rule for solenoids is you wrap your fingers in the direction of the current, and you find that the magnetic field will be coming, not that direction, outward. Okay, there we go. Outward. So it comes out of the page towards us. And so that is the idea of how you find, using Ampere's Law, the magnetic field of an infinitely long cylinder, basically the same as a solenoid. So what we did then was we used the symmetry of our, we used our Amperian loop to cut through the middle of it, so that most of the loop canceled out, and the only part that we really had to look at was one little line. Hope that helped. I will see you guys on the next one. Thank you much. Bye.